Hi, my name is Marco Faroni, and I'll present our work on online adaptation of sampling-based motion planning with inaccurate models. Manipulation with physics simulators, or deep models, always come with modeling uncertainty. When we use these models for planning, the mismatch between the simulated and the real dynamics can lead to failures during the execution. We want to find a way to update the planning strategy online, according to the observed behavior of the system, but without retraining the whole model. In a nutshell, we start by planning and executing a trajectory that minimizes the nominal error. Then we stop as soon as the robot deviates too much from the nominal path. Then we measure the actual error and the local context of each executed transition. We update the cost function and the sampling bias to avoid transitions similar to the previous bad transitions. And then we go back to step 1, that is, we replan with the new cost function and sampling bias. So let's see the method in action with a simple 2D navigation problem with drift. So in the yellow area, the robot has a small drift, while in the orange area, the drift is larger. We want to avoid both the orange area, but also staying too close to the obstacle. At the beginning, we only minimize the expected drift, but this drives the robot too close to the obstacle, causing a stop. After a couple of replannings, the planner understands that it's better to stay away from the obstacle to avoid future stops. We consider now a more complex case study with a 7-dove arm moving a heavy dumbbell from a starting point to a goal area. The robot control is compliant, causing tracking errors depending on the robot configuration. We evaluate the number of replannings to get to the goal when an obstacle is on the way and stops the robot's execution. As you can see, both planners cause the robot to collide with the obstacle because of the compliant control. However, after a few replannings, our planner understands that it should change the planning strategy and avoid those stays too close to the box. In this way, it is able to find an alternative path and reach the goal with a smaller number of replannings. Summarizing, we presented an adaptive sampling-based motion planner that updates the cost function according to the measure error. The adaptation is applied to the whole search space thanks to the concept of context similarity. 2D and 7D examples demonstrate that the planner can adapt to the real observation and reduce the number of replannings to reach the goal. Thank you for watching.